Okay, so this chapter is, we started with an introduction to Newton's three laws. We looked at free body diagrams, and now we looked at gravity, we looked at friction, and now we're just going to continue marching through a couple different other examples of specific kinds of forces. Today, springs. Tomorrow, well, you're going to end up doing springs again tomorrow. But we're going to look at tension in the form of pulleys. We're going to look at elevators. We're going to look at inclines. It's going to be great. So, springs, Hooke's law. Hooke's law was named after a British, it would be a shame to just call him a physicist because he wasn't. Back in the day, nobody was just one thing. They all did everything. So he did geophysics and regular physics and math and philosophy, and his name was Robert Hooke. To give this some historical context, this is like he was born in the middle of the 1600s, died early 1700s. So this is that long ago, 400 years, give or take. And he kind of wrote the book on springs, which is kind of a boring book to write, but that's what he did. So we've got elastic forces. F elastic stands for elastic force. Oh, what is an elastic force? What does an elastic do? How do you know if things are elastic?
It can be stretched and it pulls itself back.
It can be stretched and it pulls itself back together. That's one way to look at it. Or what's the exact opposite of that? So I've got a rubber band. Rubber bands, we also call them elastics because if I pull the thing back and I let go of the back end is going to race to meet the front end. That's all it's trying to do is reform its shape. But there's an opposite to this as well. Yeah, Lena. Yeah, if you compress something, the elasticity of that object is to what degree does it want to spring back out. So if you squish an object and it pushes back out against you, you pull an object and it wants to slam back together, that is a measure of elasticity. So an elastic force is a force that works to return a distorted object with a T, not a K, back to its rest state. An elastic is totally content to just sit on the page. If you don't touch it, it won't touch you. You grab it, you pick it up, you pull it back, and now all of a sudden you've got something that can hurt. Because it just wants to get back to its rest state. We've got a name for this rest state. The fancy name for rest state is equilibrium. And elasticity is just the degree to which whatever substance you're looking at is able to do this or not. Elastic bands are a simple example, but we've got all sorts of examples. If you have glasses, there's springs in the arms, or if you've ever built a trampoline, you know that those springs, a spring on a trampoline really wants to just compress itself. That's why it's able to be so bouncy. Your skin, thankfully your skin has a degree of elasticity as well. If you weren't able to stretch your skin and have it come back, pregnancy would suck more than it does already. Working out would be really difficult because as you build muscle, if your skin can't stretch, the muscle would have nowhere to go. Either you'd crush your skeleton or you'd rip through your skin. The extreme version of the Incredible Hulk. Like all sorts of different kinds of substances have different degrees of elasticity. So I've got a whole list of examples here. Springs. And there's different kinds of springs. Some springs are really, really strong. They really want to come back together. Other springs, less strong. Slinkies are a great example of a really, really weak spring. They are springy enough that they will noticeably come back together if you just let it sit on the desk. But they're not so strong that my 3-year-old, couldn't pick it up and distort it past its restoring point. Like, hands up, have you ever seen a slinky that has been demolished to the point of it's no longer a slinky? So there is a maximum elasticity to these things as well. So springs, rubber bands, slinkies. What's a slinky?
I don't see that one. I used to. It's a child's toy. And they crawl down. Oh, is that it? No. And they crawl downstairs.
So it's like it's a loose spring, and then that English we call that a slinky. That is more direct, very German of you. But that's effectively what it is. There's all sorts of sports. Every single sport that I can think of, except for maybe some of the standard like feats of strength kind of stuff, are dependent on some form of elasticity. In hockey, the elasticity is in the stick. I'll show you some examples of that today. If hockey sticks don't have some form of elasticity, stuff doesn't function. Yes? Yeah, your muscles absolutely have a degree of elasticity to them. If you take them past the point that they're able to restore, they will tear. That's why that's the whole point of stretching, is to build on to relax some of that elasticity. You were talking about ACLs. That's a tendon. They have substantially less elasticity. They are not designed to be super elastic. That's why they snap. That's another tendon. So the tendon, if I'm not mistaken, is what attaches the muscle to the bone. Is that right? Yeah. Tendons attach muscle to bone. Muscles are designed to be elastic. Tendons are not. So if you exert yourself to the point of exceeding that, that's why people tear their ACL, MCL, Achilles tendon. We've all seen those. If you haven't, you should go YouTube these horrific, like, tendon snapping incidences, or you hyperextend a knee and now you've torn some of the stuff inside there. Watching someone snap their Achilles tendon is pretty intense. I've seen it once. It was disgusting. But it's a good example of what happens when this thing can no longer be distorted. You've exceeded the elasticity for some of these objects. Yeah, some of them are brutal. Liam is talking about, was that McWhinney?
Yeah, he tore his bicep in our gym class.
Last year, wasn't it? Like last spring?
No, it was grade 9. He went to do
it was that year?
All of a sudden you could see his bicep shoot up in his arm. It was horrible.
So it wasn't the bicep itself that tore, it was where it attached.
It was the tendon.
It was the tendon.
Tear, but it definitely shot up.
Yeah. So it became, well, and the shooting up, it's exactly what we're talking about. If you watched his bicep slinky up his arm, that is the elasticity of the muscle restoring it back to where its equilibrium state would be.
There's not much pain to it either. You're sitting there for like almost a week with it just
kind of
going to the hospital.
That's unwise. The kids keep going here. Other sports equipment, bats and balls, hockey sticks. Your skin is a good example of something with an elastic property. Yes, here, you had your hand up. Okay. And to a degree, all of these elastic objects follow the law put down by Robert Hooke. His law said this: the amount of elastic force, so how badly an object wants to come back together, is proportional to, and so I'm going to write this down here, the force, and I'm going to call it big E. Proportional to is this symbol. Looks like your Greek letter fish. It's proportional to something. Just by talking about this rubber band, let's see if we can figure out what it's proportional to. So the rubber band sits. Nobody is scared of the rubber band. I take the rubber band and I'm going to point it at Lena. Is this scary at all? I'm just pointing it at you. If I let go right now, is anything going to happen? You know what? I won't point it at you. I'll point it so you can see what I'm doing. I'm pointing it at the board. Is anything going to happen now if I let go of the spring or the elastic band? If I let it go right now, it just falls back down. Why? I didn't, well, tension's a whole other beast. I'm not distorting it. All I'm doing is holding the rubber band at the length the rubber band would be normally. I have done no, I have not, because an elastic force is a force that works to return a distorted object back to its rest state. This is the rest state for the rubber band. Yeah, I can't see, so I'm gonna stand up. This is the rest state. It's that long. If I hold it at its length, it's not gonna do anything. But as I start to pull it back, I'm distorting it past its rest length. So if that's its length, I've distorted it maybe 2 centimeters. And if I let go, it's just gonna flop past my fingers. Not an overly extreme restoring force, but if I pull it way back, and now I pointed at someone, I'm not going, but if I did, this would be a whole lot scarier than this. This might not even make it to Lena. This would absolutely make it to Lena. This would probably make it to Yad. Yep. You can shoot it back if you'd like. I wouldn't mind having my rubber band back. Oh. Let's try again. Shoot me again. So what he discovered was, in playing with these things, perfect, is that the amount of elastic force present is proportional to the amount of distortion. Which we will call X. And so Fe is proportional to X. And this value here, just so we're really clear, is the total stretch minus the equilibrium length. Equilibrium length. So just the distortion piece. If you just pull the thing to its normal state, there is no stretch or there is no distortion, so there is no force. Now, when in math we say that something is proportional to something else, what that means is, in this case, Fe is going to be equal to this extension. So proportional doesn't mean equal to. Proportional means you're equal to up to some multiplier that we're going to call K. So what this means is the elastic force changes with the extension multiplied by some constant value. So we call, in Hooke's law, this value that we're going to call K, K here is measured in Newton meters, and K is, just like mu was for friction, K is a property of the individual spring you're working with. So every different spring is going to have a different value for K. We call this thing the spring constant. And just like mu was for friction, the coefficient of friction, experimentally verified, spring constants are experimentally verified for a given spring. So this is what you guys are going to do for me tomorrow. I'm going to hand you some springs. You're going to find me spring constants for those things. So K is spring constant. Here we've got it written as delta X. You almost never see it written as delta X. It's just always written as X. X is the distortion from equilibrium, which I wrote down here before as total stretch minus the equilibrium length. So like friction, just a very specific, everyday sort of force that we take for granted in a lot of ways. For those of you who are driving, I don't know how many of you stop to thank your shocks or the elasticity of your tires on a regular basis. But if you don't have those, your ride is a lot less comfortable than it would be, for example. Something we take for granted every day. Spring forces. So I'm going to do this example here on the right. I want to do this one first. Before I do that, I want to show you a video. Because not everyone's into hockey to the same degree. So I just want to make sure that you guys have a chance to see this video. I don't think you need the audio. This is an example of a fairly straightforward, common act in hockey, the slap shot. So some of these are real players, some of them are not. And what I want you to notice in these shots, so this guy here, this is Zdeno Chara. He has since retired. He was the tallest player in the NHL for a long time. And at one point, he also had the hardest slap shot. So this is at the NHL All-Star hardest slap shot competition in slow motion. So you get a chance to see what's actually happening in the mechanics of one of the most terrifying things to stand in front of in sport. So watch his stick here. It is straight until it hits the ice. This is Patrick Kane. So you can see this is the mechanics of a slap shot. Slap shot, the stick is actually going to hit the ground before it reaches the puck. And you can see here the stick bends. So a hockey player will drag their stick along whatever surface they're playing on up till it reaches the puck. The stick gets raised, and the elasticity of the stick brings the stick back to shape and gives the puck a fling that is beyond what that person would be able to shoot it at normally. Here's another perfect example. The stick, if it were straight, would be out to here. For those of you who've ever watched hockey, when we're talking about flex in a stick, the sticks, if you go buy a hockey stick, there's a flex measurement, a value to that stick. And it depends on what it's made of as well. Wood and graphite sticks will be different. The flex is how hard it is to do this bend. And the harder it is to make it bend like this, the harder it's going to snap back into place. So it's the equivalent idea to the spring constant here. So you get these ridiculous bends. So you get a shot that can move way faster than it would normally. This is Phil Kessel, who's not playing in the league right now. But you get a shot that would be way harder otherwise, or than it would be otherwise if the stick didn't have any flex. So at one point, there was a dude, Al MacInnis. This is from when I was growing up. He had the hardest slap shot of his time, and he did it using a wooden stick, which is kind of insane. His wooden stick had a spring constant of 850 newtons per meter. This is the K value. And we want to figure out what is the distortion on the stick if he is able to exert 525 newtons while taking a slap shot. So this then is the elastic force that we're talking about, because if he's able to exert 525, the stick is pushing back at that same value to try and restore itself. So you've got a situation where you have a stick bent like this. That's a really kind of bad drawing. There's a wildly oversized puck. And once the shot is done, the stick is straight again. And this distortion right here is what we're looking for. So what is the distortion of the stick? How far has it bent back if he's applied this kind of force? So the way that these things work is that, at least with a hockey stick, because of the direction you're working at, your applied force is equal to your elastic force. Same idea when you're building a trampoline. The force that you're applying to stretch the spring is, if you're holding it there, equivalent to the force that the string is trying to pull you back. So in this case, Al MacInnes's applied force was 525 newtons. Elastic force is given to you by the spring constant times the distortion. And we are told that the K value for the stick is 850 newtons per meter. If you run this calculation, we're going to solve for x by dividing by 850. If you run that through your calculator, you're going to find that that extension x is going to be equal to 0.618. Those are units of, what are the units on that? Take a look at the other units in the question. What are the units on that distortion? Meters. The spring constant is newtons per meter. The force is in newtons. This extension's got to be in meters. And so if I go back here a second, what that's telling us is the distortion here is 0.6 meters, which is about 60 centimeters, so over 2 feet, or right in the neighborhood of about 2 feet of extension, or sorry, distortion, which is similar to what is being demonstrated here by Phil Kessel. Let's do another one. A student stretches an elastic band with a spring constant of 50 newtons per meter by 15 centimeters. How much force are they applying? Or equivalently, what's going to be the elastic force trying to bring that rubber band back together? So here's what's going on. You've got a rubber band. There it is at its rest state. And then we stretch the thing. This is it stretched. Now, we don't know what the equilibrium length is. It doesn't matter what the equilibrium length is, because the wording of the problem tells us that a student has stretched it by 15 centimeters. So what that means is this value here, the stretch distance, or the distortion is the language that I've been using, this is equal to 15 centimeters, which is going to amount to 0.15 meters. This is the stretch, this is the distortion that we've been talking about. So the applied force outwards, because the rubber band at this point is inherently stationary, the applied force outwards and the elastic force inwards are going to be equal to each other. The rubber band's not moving. So if we want to find how much force they're applying, we just need to find the extension, or sorry, the elastic force for this extension. So this is true because it's not moving. Acceleration is equal to 0. So we can say that the elastic force, Kx, is equal to the applied force, Fa. We know K for this rubber band is 50 newtons per meter. And the extension was 15 centimeters. Because this is in newtons per meter, that 15 centimeters needed to be converted to meters, which I did already. So what is the applied force required to make that happen? Fa is going to be 50 times 0.15. What's that going to be? .5 newtons. So not a lot. To give you guys perspective on what that would look like, so I could take my rubber band here, grab one of these Newton scales. This guy. So I got my rubber band here. Stretching this guy with 7.5 newtons. We take the rubber band out to there. That is 7.5 newtons on this rubber band. It's actually kind of long. More than I thought. That's what that looks like. Okay. We'll do one more example and then we'll call it a day. Call it a block. A 65-kilogram girl sits in a redneck slingshot. Hands up if you know what a redneck slingshot is. Okay, another video. Amazing Race. Yup. Canada. Watermelon. Here we go. So, I hope you've not seen this video before because it's awesome and I want to show it to you for the first time. Okay. So, this is a redneck slingshot. So, it's just a really big slingshot. So big, I mean, you could, in this question that we're going to do, a person's going to sit in this, but this woman's launching watermelons. This was part of Amazing Race Canada. This was on TV at one point. It was awesome. So you pull the thing back, you let the thing go. On a full-on redneck slingshot, this is big enough to launch a person. And the beauty of Amazing Race, for those of you who've never seen it, is once someone starts a challenge, they have to finish it. They cannot swap out with their partner. So with what you're about to see, this person had to suck it up and finish. Watch with me. Okay, so she's got a fantastic extension here. Form is great. So the elastic force, the way she launched it, well, let's watch it in slow motion, shall we? The way she let it go, the thing flipped over in like the pocket, flipped over, and as the watermelon went out, the elastic force caused this thing to flip around and drive it right back into her face. It's the perfect kind of question. And she had to finish. So she's definitely concussed at this point. Yeah, the replays are just perfect. This is a redneck slingshot. And I'm really happy that I was able to show some of you this. I feel quite badly for her. You, her friend, you have to finish. Boy. So, redneck slingshot. A 65-kilogram girl sits in one of these things that has a spring constant of 10.5 newtons per meter. What that means is, for every meter you want to extend this thing, you have to exert 10.5 newtons of force. If the sling is stretched 45 meters, that's incredible. What is her initial acceleration when released? So, here's what we've got. We're going to draw a picture. You've got the slingshot. The thing has been stretched. We got a girl sitting in the thing. There's a normal force acting upwards. Gravity's acting downwards. And at the moment she's released, the only other force acting on her is the elastic force along that path. So at that instant, there is still a normal force, there is still gravity. They are equal, they are opposite, and they are not in the direction she's accelerating in. So when we set this thing up to find her acceleration, if F net equals ma, the only force acting on her, causing her to move at the moment she's released here, is that elastic force. So Fe is going to equal m times a. Well, elastic force is kx, so kx is going to equal ma. We are told that k is 10.5 newtons per meter, and this thing has been stretched by 45 meters, which is insane. That's half a football field. Well, yet the rednecks do some crazy stuff. The mass is 65 kilograms. What's the acceleration? The beauty of a question like this is it can be extended really easy. Because once we determine her acceleration, she's just a projectile. We could find out her acceleration. We could find out how far. I could ask you to find the range of her flight through the air. We can do all sorts of stuff with this. At this stage, what's her acceleration? You punch that into your calculator. What are you going to get? Has anyone done this yet? While I was chatting. Yeah. 7 point. You sure it's 2.6? It's not 2.6 something. That should round it to 2 points or 0.27. Meters per second squared, which doesn't sound like a lot, but it is. Sorry? It's 26 kilometers per hour squared. This is an acceleration, not a velocity. What this means is that every second she's traveling at this acceleration, she's going to increase her velocity by 7 meters per second. So in the first, so you said here today, you said this was 20 what? Okay, so that means after 1 second, she goes from not moving to 26 kilometers per hour. So in a second, she's now accelerated to school zone speeds. After 2 seconds, she's now going 60 kilometers per hour, roughly. This is an impressive acceleration. Okay, tomorrow we're going to do the spring constant activity, where I don't give you the spring constant, you got to go find the spring constant. What I'd like you to do, there's only 5 minutes left, don't pack up. I want you to do 2 questions. I just want you to do question number 1 and question number 2A. 1 and 2A. You can get these done in the time you have. Don't pack up. Syra, I want you to do 5 minutes. I want you to do these 2 questions.
Is there a review sheet I can get for kinematics?
You bet.
I'd like to do
Pretty sure I gave it to you already.
not the review sheet.
You sure?
Yeah.
I was pretty confident I did.
But I can get it.
Oh, that's really sad.